direction that is always accompanied by a, yeah. So I'm sorry I forgot to begin the recording, but it's been nearly 15 minutes we began. Yeah, now the recording has begun. So what I was talking about was whenever there is a difference in two directions, that's represented by an angle, say theta. So in 2D case, we have to consider angles as well. But there is a way out where we can study collisions in a more effective and easier way. However, we'll just examine both the procedures. So in collision, we'll study two type of frames. One is called the lap frame. Another one is called the center of mass frame. Okay. In my very first lecture on this topic, I mean on CC2, I told you that depending on our intention or our use or our application, we can classify frames. Okay, like we had inertial and non-inertial frame. That's a different thing. Here, lap frame and center of mass frame. These things are very important tools to study collisions, specifically collisions. So what is it? First, you have to understand that no matter what the bodies are, how heavy, how small, light they are, we can always represent them in terms of three coordinates. I know you are studying relativity in parallel with this, and have you studied space-time, something called space-time? Did you study it till now? Something called space-time, four-dimensional space. Thankfully, you didn't. Else you would have been okay. Okay, Shubhay, for the time being, we may hear it's a rumor. Okay, it's not. I mean, for my class, you think it is a rumor. Else you would get confused. Uh, Thankfully, you most of you don't know it. Okay, so a particle can be represented into represented by three coordinates x, y, z. Hmm. So now, say the origin of this coordinate system is O. Coordinate system is an imaginary thing. There's no one has planted it in the sky. You are thinking it that way. Like you were, I gave that example of a boy traveling in the train. The window can be the frame of reference to him. With respect to that, he is measuring everything. So if O is, or that is the origin, is rigidly fixed. Rigidly fixed means it can't move at all. Fixed to the laboratory, then we call it the lab frame. Suppose you are sitting here, this is your coordinate system. If its origin is fixed to the lab means where you are doing the experiment, laboratory, and we would call it the lab frame or the L frame. As simple as that, you are sitting in the lab and you are looking into an experiment like that. But if the origin is rigidly fixed to the center of mass of the system, then I would call it the center of mass frame, or in short, C frame. That is, suppose you are looking into collision of two bodies, these two. Now, suppose the center of mass is somewhere here. If your origin of your frame is fixed at the center of mass, then it would be the center of mass frame. As I gave you the example, think that you are standing between two trains. Two trains are moving towards each other on the same track. Don't try to do this, however, just imagine. And you are standing at their center of mass. That frame would be the center of mass frame. And we will see what is the, advantage of taking the center of mass frame into account. Why out of the blue we are fixing our our coordinate system at the center of mass? We'll see that. So is anyone having any doubt regarding these two kind of frames? Do you understand what the two frames mean? Please respond. Okay, fine. So why center of mass frame? Why the C frame? The L frame is, yeah, knowingly or unknowingly we consider that frame only. So I hope you remember the position vector of the center of mass. It was given by R vector. Just remember that picture. The origin, system of particles, is the center of mass. Then what did we say? R is the position vector of the center of mass of the particles, say O dash. So if I am taking my origin at the center of mass only, then R would be 0, isn't it? Origin is that point from where we are measuring whether a point is, how far it is, whether it is towards my left or right, up or down, or at what angle it is. Now if I fix my frame at the center of mass only, and I'm trying to look at the center of mass with respect to that, it would be 0, isn't it? Suppose there is a tree, you're standing here. So suppose the base of the tree is the origin, and your location is suppose A. So with respect to the origin, say you are at 1 feet to the right. Now what I did, I am calling this A point, that is where you are standing, that I am calling as the origin. So now what would be the distance from origin to you? How far are you from the origin? You are in the origin itself. Hence, it would be 0. Clear, everyone? Is it okay with everyone? So R is 0. So therefore, what is the velocity of the center of mass? dr dt, obviously. That would be 0. R is 0. Now, so what? Velocity of center of mass is 0. The thing is, if you remember one important conclusion, that the total linear momentum of the system is equal to the linear momentum of all the particles concentrated at the center of mass moving with velocity of the center of mass, and mass equal to sum of all the individual masses. That is, we know that the linear momentum of the system. Is it okay now, Shubhayu? This is also a difference in reference frame, because where from I am looking into this, I am seeing the copies. Perfect. Anyways, anyone is having any problem regarding my orientation of the copy? Please tell me whether I have to shift it to the left or right. Okay. So what is the linear momentum of the system? We know that it's equals to mv, m being the total mass. So v is 0. That means total linear momentum of the system is 0. That's why C frame is sometimes called as the zero reference frame. This may be asked in the exam. That why the center of mass frame is called the zero reference frame. Actually, 2D, 3D cases are much more simplified if we consider this C frame. However, we'll be doing the L frame as well to see how comfortable it would be to work in the C frame rather than the L frame. So another thing we know that if the total linear moment of the system is P equal to mv, also we saw that about the equation of motion, it would be sufficient if we see the equation of motion of the center of mass, isn't it? Just think, remember that example, a boy was throwing a bat, about the example of a ballet dancer, that the center of mass is actually the trajectory of the entire body. Okay, so now if there are no external forces acting on the system, which we take most of the cases, then what would be the force on the system? It would be dp dt. If this force is zero, there is no external force acting on the system, then we can say P is constant. And P means what? mv, that is constant. That means V is also constant. Now what does it mean? A velocity is constant? It means it's uniform velocity. That means with respect to the left frame, the center of mass frame will be moving with a uniform or constant velocity. Hence, the center of mass frame is also an inertial frame. Considering the left frame as approximately inertial one, we can say that the center of mass frame is an inertial frame as well. Okay, hence we can apply the Newtonian mechanics to it. So is everyone okay with the two frames? Expect questions in the exam from this part, okay? In any exam. Your semester exam, unit test, or maybe if you sit for any competitive exam. Okay. So you can get few short questions from here, that why this frame is called the zero reference frame, show that it is an inertial frame, then define center of mass frame. Everyone has copied. Shall I turn the page? Use another page, I think. Yeah. Now let us. I don't think we can do much regarding inelastic collision before the vacation. So now let us take the case of two-dimensional, perfectly elastic collision. Let us study this. We have already studied the one-dimensional case. So this thing now I will study by comparison. That means I'll do a comparison, like I will be seeing looking into this for both the left frame and center of mass frame cases. So first, let me analyze it from the left frame. Next, I will do it from the C frame. This thing I doubt we have to do tomorrow. Let's see. So anyways, we have two masses M1, M2. So M1 is moving with a velocity say U1, and M2 is initially at rest. Okay. This is the case before collision. What happens after collision? This was the line along which M1 was moving. It would have been moving had there been no collision. After collision, say M1 moved the velocity v1 along this direction, and say M2 moved with the velocity v2 along this direction. Typical example of the carrom. Okay. So what we have to do? We have to analyze this, and whenever we'll be analyzing this kind of cases, we have to do measurements. So we will think that this is my x-axis, and this I will consider as my y-axis. Okay. So you can see the direction of v1 on the x-axis is some angle say theta1, and the direction of v2 makes an angle theta2 with the x-axis. You may say that, sir, why are we doing this thing? I mean, what's the point of drawing the two axes and then writing theta1, theta2? The thing is, my friend, that you have to remember in collision, two things you have to study, two laws mainly. One is related to the conservation of linear momentum. Second is that of total energy. And I think everyone is still remembering everyone still remembers the fact that linear momentum is a vector. So whenever we have a vector, say a vector making a direction angle theta with one direction, then we can resolve it. The two perpendicular directions, the direction with which the angle is being made, we can call that one as the cos theta component of the vector, and this one we'll call the sin theta component. Same thing we'll be doing here for the momentum. Okay. Is it clear, everyone? And another thing I have to keep in mind whenever I'm considering axis as x and y, I have to remember the norms of the measurements. That is, if something is below this line, its y value would be, y coordinate would be minus, and if something is to the left of this line, the x coordinate would be minus. Let's see. Let me redraw the picture. So first I'm drawing my coordinate system. You can see nothing can move to the left of the system. Okay, it can either go up and down. Let's see how. Still, I'm just drawing it. Say x origin O, x dash, y O, y dash. Think it this way. theta 1. Yeah. What is this momentum? This momentum is m1 v1. Okay. I'm dropping the vector sign for simplicity. You may keep it. So what is the cos component of this one? This thing. So along this direction, if this vector is making an angle theta 1, then this would be m1 v1 cos theta 1. Isn't it? You can keep the vector sign as well, no issues. If it's difficult for you to understand, you can keep it like this. And what is the sine component of this vector? That is along this direction. That is m1 v1 sine theta 1. I'm just looking into the component. Okay, I'm not writing the vector sign. This also you may simply remove. Think component wise. See, it's a vector A vector. What is this part? It is A cos theta. This much is A sin theta. Clear, everyone? Similarly, it is m2. So this is the direction of the momentum of the second particle. That is m2 v2. See, the angle theta 2 is made along x-axis. So along this direction, we will have the cos component of this momentum, and along this direction we will have the sine component of the momentum. See if you got it or not. What I did, I said I have a vector say A making an angle theta 1. I am calling this, I am saying that along this direction I will have A cos theta 1. Along this direction I will have A sin theta 1. And I have another vector, say B, making an angle theta 2. I am claiming that along this direction I will have B cos theta 2. And along this direction I will have B sin theta 2. Is it okay, everyone? Please tell me if you have any problem. Don't feel shy. Is it okay? So what did we do? See, we just resolved the momentum into either x or y directions. Why did we do that? There's another reason. See, initially the first particle was moving along x direction, and this direction is an arbitrary direction, isn't it? And it would be always wise to consider everything in terms of one single direction. Then it would be easier for us. Then simply we'll just add or subtract. If it is along the same direction, we'd add. If it is along the we would simply subtract. So now what we'll do, we'll write the conservation of momentum conditions. But we have to go axis wise. Conservation momentum first along x-axis. What is the condition? Total momentum, I mean linear momentum before collision is equal to total linear momentum after collision. So along x-axis, what was the total linear momentum before collision? Only this particle was moving with a velocity. So what was the total momentum before? m1 u1. What is the total momentum after collision. See, along x-axis we have two components, and they are along the same direction, so they will get added up. So this one plus this one. So see, everything is along the x direction, so I am not writing the vector sign. I told you last day also that the unit vector for each and every term is the same. So I can simply write it in terms of scalars. So what is the situation along y-axis? What was the total y-axis before collision? Can anyone tell me from the diagram? What was the total linear momentum along the y-axis before collision? Anyone? Yes, Nirupan, why are you so late? Did you have network issues or something else?
Sir, I was traveling, sir.
Oh, okay, okay. Are you coming to the college?
No, sir.
Okay. By the way, anyone can tell me what is the total linear momentum along the y-axis before collision? Did the particle M1 had anything along the y-axis before collision? Does the picture convey anything that the body had any velocity along the y-axis before collision? So what should be the momentum before collision along y-axis? It should be 0. How to check momentum? Whether the direction along which I am asking, whether the body has a tendency to move along that direction. Likewise, see here. Here, at this point, we can see that the body has a tendency to move this way as well upwards. That is, both x and y momentum will be there. So you can see before collision there was no momentum along y-axis. After collision, what we are getting? Two momenta, but they are in opposite direction. The upward one, by the norms of coordinate systems, we know that we have to take that positive. Another one would be negative. That is, this one is equal to this one, isn't it? Then only you can cancel the two things. Your right hand side is 0. That means what? The left hand side, the both the terms should be equal. Then only it will be 0. Okay. So these two equations are coming from the conservation of momentum. What about the conservation of energy? Or what about the, we can say, the energy condition or the energy equation, we can say. So for perfectly elastic case, what we know that the total kinetic energy before collision is equal to total kinetic energy after collision. So what was the total kinetic energy before collision? Half m1 u1 square for the first body, which was moving with u1 velocity. Second was a couch potato, so it's 0. After collision, the good thing is that you need not to consider the components here. Simply u1 square v2 square. That is, it's not like v1 sine 1 theta square, sine theta 1 square, not like that. So see, we have three equations, but what are the unknowns that we are having? We have four unknown quantities. How? What quantities we don't know? We don't know v1, v2, final velocity. Hence, we also don't know theta 1, theta 2. So you know that you have studied in algebra in your school days that the number of unknowns must be equal to or less than the number of equations at hand. Then only we can completely solve the problem. I have say quadratic equation. Equation in x and y. So 4x plus 3y equal to 5. Just one thing I have. This, suppose I have this equation. So I cannot completely solve it. What I can do, I can just substitute. I can just write x in terms of y and so on. But I can't write x equal to how much, y equal to how much. Same case is here. I have only three equations, but I have four unknown quantities. So in general, we cannot solve it. Yeah. Now, if I give you some special conditions like v1 and v2 are equal, or theta 1 is 90 degree, theta 2 is 60 degree, that is a different case. But we should not rely on those cases at the first place. So how can we solve this thing? This problem can be scrutinized easily in a bit simpler manner in the center of mass frame. Okay, we'll study it tomorrow. I'm just giving a small hint of what it is. So first thing that we'll be doing is we'll measure the velocity of the center of mass of the system. Obviously, this has to be measured with respect to the left frame. Because with respect to center of mass, its velocity always would be 0. So you know this is the formula. That is the position coordinate vector is how much? m1 r1 plus m2 r2 by sum of mass. Time derivative of that will give us this. Okay. So in our case, what we have? u2 is 0. Therefore, our v is u1. Okay, so tomorrow now we'll proceed further to see how we can get some deeper insight without hampering the physics. Okay, so tomorrow at 8:40 let's meet. I think that would be the last class before the vacation. Okay, thank you everyone then. If you don't have any doubt, we may conclude the class. Or if you have any doubt, you may ask. Okay, thank you then. Take care everyone.